Hello everyone, my name is Sing Kao, or you may know me as Jacob, and this is my presentation for my Math 2B Linear Algebra class honors project, and my topic is applying linear algebra in dating app recommendation system using cosine similarity. So this is a little bit about myself. My name is Jacob Kao. I major in data science and I'm transferring to UC Berkeley this fall quarter. So my topic, dating apps, and how does it work? Well, to begin with, I want to tell a little story. I am 27 years old, I'm a male, and well, I've been single for quite a bit. So naturally, I have some experience in using dating apps throughout the years. And I have some good and bad experiences. However, there are some times when I'm just not getting any good results on the dating apps, and I feel quite upset, to be honest with you. And I asked around with my friends and peers, and I was surprised that many people shared the same feeling. And I started wondering about how it worked behind the scene. What is the algorithm that running behind all these apps? So this project is to examine and to learn about this particular algorithm that's used in some particular dating apps, especially Hinge, which is called cosine similarity and collaborated filtering. And as you see in that formula here, it's a cosine theta equals to the dot product of A and B vectors divided by the length of the product of A and B. All right, let's talk about the algorithms of dating apps. There are three major players in the market, which is Tinder, Bumble, and Hinge. Together, they dominate about 70% of the online dating market. They serve over hundreds of millions of users every day. And actually, these dating apps, they like to hold their algorithms in secret. The users will not manipulate game or manipulate the system. However, different dating apps use different algorithms. And from the information that we know, dating apps such as Tinder and Bumble, they use a system called ELO ranking system. And for Hinge, they use a cosine ranking system featuring the collaborative filtering. You might heard of ELO ranking system in chess. In chess, each player is given an initial score. And then each player competes against each other, and their score increases or decreases depending on whether they win or lose in those games. Also, their opponent's ranking. The dating apps takes a similar approach by likes and swipes. The more people swipe right on you, the higher your scores become. In turn, you will see other users with similar ELO scores shown to you to potentially match with you. However, the cosine ranking is a little different. It does not put the users against each other. Instead, it looks for similarity between the users. Cosine ranking measures the similarity between two vectors based on how close or far apart the angle between them is. If you have used a dating app, you might know that when you create a profile, you will have to put in a bunch of personal informations, such as your hobby, job, relations, sexual orientations, political affiliations, your favorite book, your favorite food, your favorite movie, so on and so forth. All of this data will be collected. Each user then be represented as a vector containing all this data. Using the cosine ranking, the system can determine how similar one user is to another user. Okay, let's talk about the mathematical proof of cosine similarity. Suppose we have two vectors, vector u and vector v. We'd like to know how similar they are by measuring the angle between them. If we drop a perpendicular line from one vector to the other, we create a right triangle. Since the cosine is defined as adjacent over hypotenuse, it seems like it's a very useful tool to find the angle. So the thing is that vector u may not have the same length as the adjacent side of the triangle. So we introduce a scalar k that scales u to a new vector r, let the perpendicular vector be w. we know vector r and vector w are perpendicular, their dot product equals to 0. And because we know r equals to ku, we can rewrite this formula because r equals to ku and w equals to v subtracts r. And then we rewrite the r, we substitute all of them, we get this new line of formula. And then we can do some basic algebra. We divide all of them with a k, and then we can simplify in this. Now we look for k equals to the dot product of u and v divided by the dot product of u and u. Now we can try to substitute this result into the cosine formula that can simplify to the cosine similarity equation. So we know cosine is adjacent over hypotenuse, which is the length of r divided by the length of v. Then we can substitute it, and then we know k is just a constant equals to this thing we just got. We can move it out because it's just a constant, and then we have this formula. We know that the length of u equals to the product of u and u, and take a square root. So we do some, again, basic linear algebra, remove them, and then rearrange them. We know this is this. So we can rewrite this formula to cosine theta equals to the dot product of u and v divided by u, the length of u and the length of v. Very well. Using this formula, we can find angles between the vectors. Like we can just do the r cosine, and then we can easily find the vectors. We can easily find the angle. However, if we only care about finding a good matches, we don't really need the angle. We just need to know the value of cosine theta. So we can instead just look for the cosine theta and between the range of 1 and -1. If it's 1, it's a perfect match. If it's 0, it's perpendicular. And if it's -1, it's the opposite match, which is probably the worst match. Another useful observation comes from rewriting the formula. If we divide a vector by its length, we create a unit vector, which is a vector of the length 1. So we scale all this vector to 1. After I normalize the vector, the cosine similarity becomes simply the cosine theta equals the dot product of the normalized vectors. This insight is the formula behind many of the recommendation system. Rather than computing the angles directly, the normalized user vectors and calculate the dot products makes the process computationally more efficient. Now you may start wonder, well, just because we're similar to each other, it does not mean that we are a good match, right? Here is when collaborative filtering takes place. And this is how many of the other big companies such as Amazon, Netflix, and Disney recommend you any of their products. Instead of matching you directly with a similar person, collaborative filtering finds a user who has similar preference as you and then recommends the people who those similar users liked. This concept will be easier to explain with movies. Let's imagine we have 4 Netflix users, Jacob, John, Alex, and Mike. And they have all watched these 10 movies. And each of them has watched 3 more movies that none of the others have watched. Now we can compare these 10 movies that they watch and the ratings they give them and find who has the higher similarity to each other. So let's take the case of Jacob. We can calculate the length of Jacob's vector, and then we get every single one of them, and we find the length of their vectors, and then we can find their dot products. We can compare the dot products between Jacob's and the other users. And finally, we find a cosine similarity. between Jacob and each other users. And then we find that Jacob is most similar to Alex's taste. And then we look at these three more movies that Alex watched and Jacob haven't watched yet. And we choose this one that Alex gave the highest rank, which is Mad Max. Then the system will feed Mad Max to Jacob, which Jacob is most likely going to like. This is how dating apps works, such as Hinge is following a similar pattern. Instead of matching Jacob, which this is me, obviously, people say I look like Brad Pitt. So Jacob, instead of matching Jacob to someone who has a similar interest and vectors as himself, they match them with user that has a similar vectors and data as Jacob. So Alex and Jacob are similar. They have similar hobbies, and they will show that Alex has matched with Amy and Sophie. Then the system will feed Amy and Sophie back to Jacob, which may increase the likelihood that they are going to match. So you can see, because they look the same, so they are probably going to like the same sort of females. Well, for this project, I actually made my own dating apps. I created a dating app for DENZA students, which I call Dating Enza. I think making this app was very interesting to me because I have never done this before. And then, well, I learned how to make this. I had fun and I learned a lot. So let's get started. Let me show you how my dating app works. So first, you put in your name. And then you put in your age. I describe myself as a man, data science major, and these are my hobbies. Maybe let's change a few things. That's mixing up a little bit, maybe. Okay, that's good. I'm looking for a woman, and let's see who we're gonna match. Oh, Lena. Sheesh, you doesn't really look like a girl, so I'm not gonna say no to you. Okay, Andre. Okay, so I like Andre. Skylar. Oh, I matched with her, and I can start chatting with her. I can say hi, and then I can go back and keep scrolling. I can say hi to this. Oh no. Oh no. Oh wow. Who are these people? And yes. Oh, and then I matched with Priya. So when I was making this, for privacy reasons, I can use some real data from real people because I cannot show that onto this presentation. So I create this. Some of these are mock data, some mock profiles. However, they still share all of these attributes, then the vectors. So I can embed cosine similarity and collaborative filtering into my algorithm. So this dating app is following this kind of matching system, which you can see here that it actually shows the percentage of your match. And then, yeah, that's the app. It's pretty straightforward, like any dating apps, and it's a really good real life application of how we can apply linear algebra into real life problems. Oh, great. So yeah, this is my slide, and this is my presentation for my finals project. Thank you very much for listening and watching this video, and I hope you learned something. Thank you. This is my citation. Goodbye.